If you have a wave that's going up against a barrier and the barrier has a slit in it, then when the wave goes through, it spreads out like you can see on the picture that's on the left there. And as long as the slit is of a similar magnitude as the wavelength of the wave, you'll see this occurring. It creates wave interference if you have more than one slit. In fact, even if you have one object that is blocking the way, the waves will still diffract around the edges of that object, causing a similar response to what we'll see with a double slit. And so we'll go back and forth between those two. But what happens as this is going on, with your wave, the waves interfere like they would for any other type of wave, but it's in a pattern format. So you have areas where they build together for constructive interference and areas where they cancel out for destructive interference. And what that will look like if we're looking at a ripple tank, is that the constructive interference has big waves that you can see, and then the destructive, you have no waves. And so having those two areas together, you can see that in the ripple tank, it gives you those lines of no waves that where you have your destructive interference, and then the higher waves with the constructive interference. And when it is with light, that same thing happens as well. So you have areas of bright light and areas of no light. And that's what we'll be using to take a look at diffraction here. So I went into school the other day and I set up the diffraction grating on an optical bench and I shined the lasers through there. Now, depending on the wavelength of the laser will depend on where those dots will show up. And so where my thumb is on the 50 centimeter mark, and you can see that the red one is, if you go about 28 centimeters in either direction, is where you have your n equals 1 for your first dots there. And on the green one, it's the same diffraction grating, but if you go about 21 centimeters in either direction, that's where your n equals 1 will show up, because red and green have different wavelengths, and we can use that to do some different calculations. So if we just focus on two waves that are coming out of the slits, right now these are the same wavelength, and as they're reaching the wall, they are in phase with each other. And so if we're talking about light here, then you can see that the dots are lining up and they're ending up in phase as they're reaching that spot. So for light, that means it'll be a bright spot, because when they're in phase, you have constructive interference, and then that will add up and become brighter. And so if we move a little bit farther, the farther out we go, you'll start to see that they're not in phase, they're not out of phase. Oh, but here we go. When we reach about out here, it ends up being out of phase as it is reaching the wall. And out of phase would cause destructive interference, and then it ends up happening that it is a dark spot that you would have in there. And everything in between, when you're looking at just double slit diffraction, has variations on what you can see there, but we focus on the bright spots and the dark spots. And so if we go out farther, they'll start to come in phase again as they're reaching the edge there, and that would be n equals 2. Be the second time that they are in phase and causing a bright spot. And that pattern would continue. If we go out farther from there, they become out of phase, and then farther they're back in phase. And so the difference happens because of the path length difference that shows up from where they are to where the wall is. And the number of wavelengths that happen, if they're on an actual number, a whole number, they're in phase, and if they're half off from each other, then they will be out of phase. In the data book, you'll see three main equations involving diffraction. The first two are talking about the interference that can occur and the path length difference in order to have constructive interference or destructive interference, and I'll show you that in a moment. And then the other one that'll show up in topic 4 is this equation here, where S equals lambda big D over little d. If you look in the Holt book, you'll see this equation, d sine theta equals plus or minus n times lambda. And this one actually also shows up in the data book, but it's in topic 9. And so if you're prepping for the exam and stuff, this one shows up in topic 9. It's still, I'll show you how these two are connected in a little bit. So if we're saying that S is equal to lambda big D over little d, how does that apply to this triangle setup that we have here? And so let's look at some equivalences. This shaded triangle and this yellow triangle, they're going to have the same ratios to each other. The angles are the same. And so we can say that this measurement here of B over B to O, this line and this line, those two would be similar to each other. And then this line and this line would be similar to each other. And so I can say that the line BO, the ratio between the line BO and the line CO would be equal to the ratio between A1 and P, and then over A1 to A2. And so those lines in themselves, that equivalence is true because these two triangles are similar. They're just of different sizes. The angles are all the same though. Well, if we take a look at the variables that we have and put them in here, BO is equal to S, so we can say S over CO is the distance between the grating and the screen, so S over D is going to be equal to A1 to P is our path difference, and when N is equal to 1, our path difference is just the lambda, the wavelength. And then over, if we look A1 to A2, that's the distance between the slits. And so as we get to that equation that we have, if we multiply both sides by big D here, cancels out there, and we end up with that S is equal to lambda D over D, using the setup that we have here. And so we can use that. One thing I do want to talk about with this distance here, this is our path difference. So if we're talking about our blue line here and our blue line here, the difference in the length of those is whatever falls right here. And when this path difference, is a whole number, so if it's 1, 2, 3, 4, exactly that, meaning that this is a full wavelength longer than this one, or exactly 2 wavelengths longer than this one, or exactly 3 wavelengths longer than this one. If that's a whole number, then that's when we have constructive interference. If the path difference here is N plus a half, so you're falling on the half, 1.5, 2.5, 3.5. If it's a half number, then it's destructive interference. And so it gets back to these equations that we were looking at here, where we have constructive interference. It means that path difference is a single wavelength, or exactly 2 wavelengths, or something like that. And when we're talking about destructive interference, we're talking about how the path difference would be 1.5 wavelengths, or 2.5 wavelengths, or something like that. So you'd have 1, 2.5, because then when the path difference is on a half wavelength, when it gets to the screen, one of them might be on the peak, the other one would be on the trough, and then they would cancel out. And so that's where you would get the darkness in there. In your Holt textbook, you have the equation that d sine theta equals n times lambda. And there's usually going to be a plus or minus in front of that, and that just indicates that it can go in both directions. And in order to have this relate to the book that we have in our data book, in order to see how it relates, we have to look at something called the small angle theorem. And the small angle theorem says that sine theta is close to tangent theta is close to theta in radians, but we're not getting to this point here on this. The main thing that we're looking at is that sine theta and tangent theta are pretty equivalent. And this only happens when you're dealing with teeny tiny angles, which we are when we're dealing with diffraction. And so if we take a look back at our triangle, and we have D is the distance between our slits, we have S is the distance between our maxima, the bright spots for the laser, so N0 to N1, and big D is the distance between the diffraction grating and the wall. And so if we say that sine theta, which would be hypotenuse opposite over hypotenuse is equivalent or very close to tangent theta, which would be opposite over adjacent, then these two here would be the same. And instead of saying sine theta, we can say tangent theta. Well, to measure out the tangent theta, this is big S over big D. And so now what we can do is we can take this and put it in for our sine theta, and we can say little d times S over big D is equal to n times lambda. And so again, on the other equation that we're using, we assume that n equals 1, so we can get rid of that. And then we can go ahead and multiply both sides by big D. And then that cancels out here. And then we can divide by little d. And it cancels out there, and it brings us to S equals lambda big D over little d. So, depending on the situation you have and depending on the information you have, whether you use S equals lambda D over D, or you use D sine theta equals n times lambda, they'll both get you to the same point. It's just that for topic 4, they focus a little bit more on this equation and keeping things at n equals 1. And this gets into more situations and more, it's just more versatile. This equation will show up in topic 4 in your data book. This equation shows up, I think, in topic 9 in your data book. So it's still there. It's just not one that you would find just off the bat. 1, 2, 3, 1, 2, 3, 4. So if we take a look at the stuff I had set up here, I was 0.52 meters from the screen there. And so D is 0.52 meters. And if I'm talking about the green dots, the green laser there, S was equal to 0.16 meters. And the green laser has a wavelength of 532 nanometers. So we can say 532 times 10 to the negative 9th meters. Nano is times 10 to the negative 9th. So we can use our equation and figure out how wide the distance between the slits here. And so we can say that S is equal to lambda D over little d, and we can rearrange that to say that D is equal to big D times lambda over S. And so we can say 0.52 meters for our big D times our wavelength of 532 times 10 to the negative 9th meters over our S up here of 0.16 meters. And when we calculate that out, we end up with the D, the distance between our slits, is 1.7 times 10 to the negative 6th meters. And so that means that between the two slits that light is shining through, the distance is 1.7 times 10 to the negative 6th meters. When you're talking about a diffraction grating, so if you're just talking about the slit distance, that would be this right there. We've got that. With a diffraction grating, it's got a whole bunch of slits that are this big, and it's frequently measured in slits per centimeter. And so if we're going to get it into slits per centimeter, the first thing we would do is take 1 over D to get slits per meter. And so we would take 1 over 1.7 times 10 to the negative 6, and that would give us slits per meter. And then we want to get slits per centimeter, and so we would take whatever number we get here, which in this case is 5.8 times 10 to the 5th meters would be our slits per meter. And so then we'll take our slits per meter, so we'd have 5.8 8 times 10 to the 5th slits per meter, and we would divide that by 100 centimeters per meter, and so we would end up with 5,800 slits per centimeter. And so just know that if it's talking about a diffraction grating, and it might give you something like this, you'll have to work between the two situations here.
Dun, 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 dun.